So good afternoon, everyone. Today we have the great pleasure to welcome Professor Heath Turner. Professor Turner received his PhD in chemical engineering at the North Carolina State University and is now department head and professor at the Chemical and Biological Engineering Department of the University of Alabama. His group uses computer simulations to investigate adsorption and reactions on surface and at interface. Their work helps guide the synthesis of new nanomaterials, identify new catalysts for environmental applications, and design unique solvents molecules for carbon dioxide separation technologies. They also use molecular simulations and quantum mechanical calculations to screen new materials for a variety of clean energy technologies. Professor Turner has around 100 publications adding up to more than 2,500 citations. He has been awarded with the National Science Foundation Career Award and a Most Outstanding Faculty Member honor by the University of Alabama. Welcome, Professor Turner. Thank you so much for being here. Please feel free to start your talk and share your screen.
Great. Thank you for the introduction. Let me see if I can share the correct screen here. Give me just a second. That look okay? Okay.
Yeah,
all right.
Great.
Okay, good. So what I want to talk about today is really more some applications that we've worked on in terms of integrating kinetic Monte Carlo into several different material platforms. And so again, this is going to be a little bit more applied, I think, maybe than some of the previous talks. I've learned tremendously from a lot of the other speakers that we've had in this series. But I'll be talking a little bit more on some of the applications. So if you're expecting to see some partition functions and free energy calculations, you might be disappointed here. But I'll talk a little bit more about several different materials that we've been investigating. So before I get started, I wanted to tell just a little bit about the University of Alabama. We're one of the oldest colleges of engineering in the United States. We're the third oldest in the country. And if you look up the University of Alabama, probably the first thing that you'll find is football and our success in football. But we're also very proud of a lot of the academic accomplishments at our university. So we're typically ranked in the top 5 in Goldwater Scholars. This is the top recognition of undergraduate students in science and engineering in the country. And then we typically rank in the top 5 in terms of national merit finalists. And then also, last time I checked, we were either the 4th or the 5th largest chemical engineering program in the country as well. So this last year, I believe we graduated around 200 or 220 undergraduate students from our program. So today I'll be talking about several different systems that we've been modeling. First of all, I'll talk about some metal nanoparticles and looking at the morphological growth kinetics of metal nanoparticles. We're also working on amorphous carbon models. I'm not going to talk about that just because of time. But then I'll talk about some of the amorphous polymer systems and looking at these applications in membranes and looking at gas diffusion in these systems. And then last of all, I'll talk about tribological film formation that we're performing as well. So each one of these materials that I'll talk about and each one of these projects I'll talk about will be going through progressively increased amounts of integration with molecular simulation methods. So the first project that I'll talk about is really just a more traditional kinetic Monte Carlo application. But then when I start talking about the polymers and the tribological films, I'll talk more about how we're starting to integrate kinetic Monte Carlo and molecular dynamics. And the main motivation is to extend timescales. So I'll start off with the metal nanoparticles that we've been modeling. And this is just a little bit of background, practical background about these materials. So metal nanoparticles can be experimentally synthesized using a lot of different approaches, laser ablation, co-precipitation. And over the years, there's been a lot of experimental progress that's been made in terms of trying to achieve different metal nanoparticle sizes and shapes and size distributions. But over the years, a lot of this has really just been developed through trial and error types of approaches. So it's very much a recipe driven approach that the experimentalists have taken. And so it can be very difficult to try to predict how to change that recipe to achieve different shapes or sizes of nanoparticles. And so this really sparked our interest in trying to develop some models to predict the growth. So in terms of the modeling work that's been done for metal nanoparticles and metal nanoparticle growth, there's been a lot of atomistic computational modeling that's been performed, but traditionally, people have approached this a couple different ways. So in one case, they might use some type of many-body potential or maybe even some DFT approaches to try to calculate and predict the energetics of different minimum energy structures. And so what they do is they try to screen through and try to identify using several different search algorithms the minimum energy structure of some of these metal nanoparticles. In other ways, some people looked at the binding of ligands on different metal surfaces to try to predict the growth or the shape of different nanoparticles that might transpire in a solution. So depending on the specific ligand, it'll bind to different crystal faces, and that might either enhance or deplete the growth along those crystal surfaces. We've used both of these approaches ourselves. These are just a couple of examples here on this slide of what we've done before. But again, these approaches really focus on minimum energy structures. And what you'll find in experiment and a lot of other kind of nanoparticle systems is very rarely is a structure dictated by the minimum energy energetics. Often it's the kinetics that's really driving the shapes or the structures that you'll find in many, many applications. So that's what we're trying to capture. So these are some of our assumptions going into this, and this is really just kind of the broader kind of modeling perspective that we're taking. So we could step up to finite element or maybe some continuum-based methods, but it really lacks the necessary atomistic or molecular level resolution that we need. Also, this is what I just mentioned before. Whenever you're looking at these nanomaterials, nanoparticles, so much of it is driven by kinetics. So this is very important to capture. And if you start thinking about kinetics, and if you're looking at molecular dynamics or quantum mechanical methods, you're very limited if you compare those timescales to the experimental timescales. Even nowadays, even as we're able to push those computational limits, you're still orders of magnitude away from the experimental systems. And so if you want to expand that time scale or extend that time scale, there are going to be some trade-offs. So, this is just kind of the natural balance between computational efficiency and model resolution. And so we're going to have to make some compromises in terms of the model fidelity if we want to make some extensions in terms of the time scale. And so at this point, what we're really leveraging in a lot of our approaches is that there's a lot of experimental data that's known. And it's a question of how do we take some of these kinetic Monte Carlo models where we know some of the information about some of the energetics, maybe a few of the kinetic steps in the mechanism, but then try to incorporate some of the experimental data to improve those models. And there's been more and more of that over the last few years in terms of some kind of machine learning and some of these other kind of integrated approaches to try to take advantage of this. So our main platform that we've been working with over the last several years has been kinetic Monte Carlo. And I'll talk a little bit about the background here and the basic algorithm. I think most people are probably familiar. It's actually a fairly straightforward framework for dealing with systems. So the kinetic Monte Carlo approach is most appropriate for systems that involve activated processes. So if you're dealing with a system that has reactions, reaction kinetics, or adsorption or desorption that can be described as an activated process, this tends to work well. The time scale tends to be inversely proportional to the fastest system events. So if you have high frequency motions in your system, like a lot of vibrations in the system, you're probably going to want to neglect or approximate those motions, because those will end up overwhelming your system and severely limiting what you can do with this approach. The trade-off with this approach is because it's a kinetically driven algorithm, is it requires a database of system events. So it's not a truly predictive type of approach. You really need to have some type of chemical intuition or other modeling information to put together and assemble the different possible events that could occur in your system. And so if those possible events are not in your database, they'll never occur in your simulation. So again, there's a little bit of trade-off in terms of the predictability. So common applications in the past, people have used this for thin film growth and probably more than anything for heterogeneous catalysis on surfaces. And so this is what the general algorithm looks like. So you can perform these simulations on a lattice or off a lattice. Most commonly, people perform it on a lattice to improve computational efficiency. You start out by calculating the probability of all those system events in your database. So in that database, you're going to have different events, and they might depend on the local configuration of your system. And so you evaluate your system, you scan through the system and look for all those possibilities that might occur. Based on all those possibilities, you can calculate the relative rates of each of those events. And then based on the relative probability of each of those events, you can stochastically select the next event to occur in your system. You make that move. And when you make that move, you update the clock. It's not like a traditional Monte Carlo simulation where you might accept and reject moves. The approach that is typically taken in kinetic Monte Carlo is those moves are always accepted, and you accept the clock as those moves are accepted in your system. You update the configuration, you go back and loop through this again until you reach some type of predetermined end to your simulation. And you can evaluate kinetic and equilibrium properties as your system progresses. So this is the first system that we started working with. So this is, again, as a reminder, this is looking at the growth of gold nanoparticles in solution. And so experimentally, the way this happens is you start out with a gold salt. You have a reducing agent. This reduces your gold salt to neutral gold. The gold nanoparticles gradually grow in solution until the bulk solution becomes depleted of the gold salt. And so there's some detailed experimental data that was available for the system. So this is, we're making some comparisons against this Langmuir paper back from 2015. And so they have some very precise information about the growth of these nanoparticles as a function of time. So they have particle size distribution. They have this as a function of temperature and also as a function of the precursor concentration. So it provides a great deal of information in terms of putting together a model to try to make some predictions about these nanoparticles. So this is what our model looks like. I'm not going to go through the kinetic Monte Carlo approach again, but in this particular system, we have several different events that are occurring. So again, we just try to mimic the experimental system. So we have this gold reduction that happens in the solvent phase. And then we have gold particles that will attach to this growing nanoparticle surface. So those individual atoms can adsorb, but they can also desorb from that surface. And once they attach to the surface, they can also diffuse around on the surface. So there's several different events that can happen in the system. There's a rate constant and relative energetics that dictate the relative probabilities of each of those events. But then these events on these growing nanoparticles are also coupled to the solution phase concentration. And we do this just with a simple ordinary differential equation type of model, just like you would find in your reaction kinetics class. So we just model the concentration of the gold salt and also the gold zero in solution as a function of time, and we couple that to the events that are occurring on the nanoparticle surface. And so these are some of the details of our model. So we have a large lattice that we work with. We start off with a gold seed. So we just start off with a very small gold seed in our system. We specify the bulk concentration, very similar to the experiments. And we start off with some guesses for some of these rates. So we have a good idea of approximately what they might be within maybe 1 or 2 orders of magnitude, just based on chemical intuition. But what we can do is we can perform these kinetic Monte Carlo simulations. They're very fast. So an individual calculation will run and we'll get a gold nanoparticle that's formed in approximately 15, maybe 20 minutes on a single processor core. So what that allows us to do is it allows us to create some feedback loops comparing our predicted nanoparticle growth curves to the experiments. And as these nanoparticles are growing, we can perform a lot of on-the-fly analysis. So we can calculate the diameter, the surface area, the volume, surface roughness. We can get a lot of information about the different facets on the growing nanoparticle. And again, we can go through this training phase and we can get a model like this trained if we have the experimental data within a day. So it can go through, you know, a few hundred loops and arrive at the pretty robust parameter set fairly quickly. So these are some comparisons. So on these graphs that I have shown here, the experiments are the dotted points, and then our calculations are shown as the solid curves. And these are at a range of different temperatures. So 45, 33, 23, and you see slightly different growth curves over several different conditions. So we've looked at different temperatures. We've also looked at different precursor concentrations as well. So again, we've looked at several different experimental variables, and we're able to do a very good job of capturing this growth. And if you look at these rate constants that we have here, and I'll try to see if I can, if you give me a second here, laser pointer. If you look at some of these rate constants that we have here, again, these are the rate constants that are fit to this experimental data. These rate constants are a function of temperature, and if we look at the rate constants versus the temperature, we get a very, very nice Arrhenius type of plot. We get a 0.99 correlation coefficient if we compare this to what we would expect with Arrhenius type behavior as a function of temperature. Again, this is some more of the comparisons that we've made versus precursor concentration effects. Again, we see very good comparison against the experimental data. And what I want to emphasize is this is not just parameter fitting. These are not arbitrary parameters. These are real parameters that are connected directly to real events. And so when we do this, we really learn about some of the kinetics of these individual events. But again, these are not just arbitrary random parameters that give us a good fit. So when we do this, we've also made predictions outside of our original fitting as well. So in other words, what we can do is we can fit at a couple of different temperatures and make predictions at higher temperatures. Or again, we can change the precursor concentrations and again, get very good agreement at other precursor concentrations as well. This is another type of analysis that we can do. So we can look at particle size distribution. This is very important if you're trying to make some of these nanoparticles in the lab. Getting a very tight particle size distribution can be very important. So if we compare our simulations here on the left, we're looking at our simulated particle sizes as a function of time. And we can make that directly, we can make a direct comparison against the experimental values. And again, we get very, very similar comparisons against the polydispersity as well. And the nice part is you can get some very nice statistics from these types of simulations, because you can, again, you can run multiple samples, multiple times, starting them out with a different initial random number seed, and again, get error bars and some good representative statistics. So as these simulations are running, you can get a lot of information that's very difficult to get from experiments. And that's really what we're at here, is not just trying to reproduce some of the experimental data, but really trying to get some information that's difficult or impossible to get from experiments. And so what we can do as a function of time is we can monitor a lot of these surface features. So depending on the relative ratio of different steps, different crystal faces in these nanoparticles, this will give you very different performance if you're using these particles in applications. So if you take some of these particles and you use them in a catalytic application, or maybe some type of sensing application, biological sensing, or other kind of therapeutic application, you'll get very different performance based on the relative concentration of these features. And so what we can do is we can get a lot of that information very precisely from our calculations. And so we can see what this looks like as a function of time. And we can also then, based on this, is we can then propose and try out different scenarios to try to increase or decrease certain features on the nanoparticle surface. So this is just an example. If we look at slightly different conditions, we can we have some control. We have some knobs where we can change the precursor concentration, or possibly the temperature or pH, and get different different surface features in the system. So with some of this fitting, one of the questions that immediately pops up is the uniqueness of the parameters. So even though we can show that these parameters are fairly robust, realistic, they seem to make sense, we've also done some sensitivity analysis to say, okay, what happens if we have a little bit of unknown in these parameters? So we do some of the sensitivity analysis where we take some of these parameters, we increase or decrease them by 10 or 20% and see what effect that has on the results. And what we'll find is that there is some impact. And so when you start really asking this question, are these parameters unique? No, they're not. So you can, there is always, in my opinion, going to be some ambiguity. There's always going to be a little bit of unknown in terms of some of these parameters, kind of based on the specifics of the system. But having these experimental results that we can benchmark against really helps refine those unknowns. So the more information that we have from experiments, the more we can narrow down, and the more unique we can make those fundamental rate constants and parameters in our system. Also, here I've just shown, so our activation barrier for our adsorption rate constant comes out to be around 21.7 kcals per mole. And so again, that's a real, that's connected to a real step, a real mechanism. And so we can compare that to some experiments. And so we can look at some of the binding of long chain diols to gold nanoparticles, which is very representative of this type of process. And we get a very similar type of binding energy compared to what we're finding in our systems. So again, we feel like these are very robust and actually predictive models versus some other kind of analytical models that you might be able to develop for these systems. So with that, I'll then move on to the next project and talk a little bit more about some other ways that we're integrating kinetic Monte Carlo. And again, as I go along, I'll talk a little bit more about more and more integration that we're doing. So in this project, we're working with very different types of materials. So here we're looking at CO2 separation. And so we're looking at different solvents and different polymers for doing this. So just a little bit of background in terms of this technology. We're looking at post-combustion and pre-combustion CO2 capture. Industrially, aqueous MEA is a solvent that's used to separate CO2. But there's some challenges to this in terms of the energy demands for recovery, solvent recovery, volatility, corrosion, and so on. So over the last 10, 20 years, people have looked at a lot of different alternatives. They've looked at activated carbon, zeolites, metal organic frameworks, ionic liquids. So we've done a lot of work with ionic liquids ourselves. But there are a lot of practical challenges that you run into with a lot of these materials, either in terms of their stability, selectivity, and probably most of the time, cost. So over the years, we've looked at different ionic liquid solvents for CO2 capture. Ionic liquids can be very selective for CO2 versus methane, or CO2 versus other species. And since they absorb CO2 by a physisorption mechanism, the recovery, energy for recovery can be lower. So that can be an advantage. But some of the disadvantages is that if you look at current solvents that are used out in industry, again, aqueous MEA is at least 20 times less expensive than even the lowest cost ionic liquids. So MEA is just dirt cheap. And so it's very difficult to try to come up with an alternative to MEA. And also, if you look at ionic liquids, one of the physical property challenges that nobody has been able to get around yet is the viscosity. Viscosities are very difficult, and so it makes it very difficult to use these in applications. And so with all of that said, we're looking at different alternatives, and a lot of our applications, we're looking at membranes. And so if you take some of these ionic liquid types of functionalities and put them in membranes, you can get around a lot of these challenges. So recently we've been looking at ionic polyimides and other types of polymers. We've been looking at ionic liquid and ionic polyimide composites as well to try to tune the behavior. So these membranes and these polymers, they have very high free volumes compared to a lot of other polymers, and that's a big advantage in these gas separation applications. But again, what we're able to do is we're able to take some of these adsorption sites and functionalities and build them into these ionic polyimides. So one of the distinguishing features of these types of polymers, the people have looked at different types of polymers in the past. There are a lot of different variations, but in these particular applications, we're looking at these ionic polyimides where the charge is in the backbone. In the past, people have looked a lot at polymerized ionic liquids, but what's really happening is they're adding these ionic liquids as pendant groups to some type of polymer backbone. Whereas in our case, the charge and the ionic liquid functionality is actually within the backbone itself. So this is a very broad space, so it makes it very challenging. And so we're really looking at, options for screening these types of interactions between these polymers and different kind of ionic liquid functionalities to look at ideal solvents or separations. So we're looking at different variables that we can turn in terms of the structure of these polymers, but then also combining them with different ionic liquids as well. And then last of all, when we're looking at separation, again, most people are just looking at adsorption. So they're looking at absorption selectivity in different solvents or maybe in different polymers. That's really just a small part of the picture. You really need to think about the kinetics of the separation as well. And that's what we're really trying to do with our kinetic Monte Carlo approaches. So again, the space is very, very broad. We've looked at a wide range of different species and functionalities, ranging from traditional ionic liquids to here. We're looking at multivalent ionic liquids as well. So again, this parameter space and design of experiments explodes very quickly when you start looking at all the parameters. But to start with, we started by looking at some imidazole-based solvents. So this is the first kind of solvent platform we started looking at. And this really kind of provided us with a basis of information to develop some of our other models. So again, people have looked at ionic liquids. Imidazoles are very similar. The main difference is that they're neutral. So they have very similar structures to some of these ionic liquids, but they're really just a neutral counterpart to ionic liquids. So they still have low volatility, much like ionic liquids, very tunable solvation properties, depending on which side groups and other ligands you add to the system, but the viscosities are much lower. So the viscosities of these imidazole compounds are 1 to 2 orders of magnitude lower compared to your traditional ionic liquids. And so we were very interested in looking at these materials and looking at their solvation properties and CO2 separation potential. So we started out by doing some benchmarking. We looked at a range of N-functionalized imidazoles. So we started out with a methyl, ethyl, and we continue that chain until we got up to about a heptyl group, or even larger. But we have some really good experimental data to compare against. And so here is a comparison of our predicted simulation densities over a fairly wide range of temperatures, and also different chemical species ranging from that methyl group, that methyl tail, all the way up to the heptyl tail. And so over a fairly wide parameter space, we're able to reproduce the densities within 1% or less. So we feel like we've got a pretty good model for these systems, at least based on some of this data. We then go on to look at some other thermophysical properties that are relevant to some of these applications. So we'll look at things like heat capacities of these solvents. This is important for solvent regeneration. We'll also predict Henry's constants, so we can compare to the experiments. Overall, we do a pretty good job. We're off quantitatively by 20 or 30% in some of these applications, but we're able to do a really good job in terms of the qualitative predictions. We get the trends very, very well. And so we feel like this is we're able to do a really good job in terms of screening the properties of these materials. So really the next step for us is really trying to understand these systems a little bit better and understand why. So if we look at the methyl chain versus maybe the heptyl chain, and they give you different CO2 absorption properties, we really want to understand why. And so we've really started looking a little bit more at the structure and the electrostatic interactions in these systems. And so we're really treating these materials almost as if they were a solid porous material. They're not, they're a liquid, but we're applying a lot of analysis techniques that you would normally see for porous materials. So we look at the fluid structure. We look at the, let me change my pointer here. So what we can do is we can look at the fluid. So this is a solvent, a liquid solvent, but we can look at the fluid structure, the void spaces in the solvent. And this is really just a static fluid structure here where you can perform this type of analysis. But what you can do is you can do this hundreds or thousands of times. Okay, so you can take different simulation snapshots, calculate that fluid structure, and you can essentially get a pore size distribution in that fluid, or a cavity size distribution within that fluid, whatever you want to call it. And what you'll find is you have this very natural progression in these solvents, going from the methyl all the way up to the heptyl group. in terms of what that pore structure looks like. And this is where the salt, or this is where the gas is going. The gas is going into these pores. And so if that pore structure changes, you're going to have very different adsorption properties. And so what happens in this particular system, as you get those longer chains are less mobile, less flexible, and this ends up being causing larger voids in the system to persist. So you get some of these larger voids in the system. And if you look at this pore size distribution, it's actually pretty small. These are actually very small pores. And so if you look at this, really only a small fraction of this is really going to be accessible to absorbates that enter the system. So this is really the tail end that we want to focus on. And so if we look at this and we make some comparisons and we focus on this tail, again, we're really just looking at this accessible pore space. We can make some very nice predictions in terms of the gas adsorption based on this analysis. So again, we can look at the relative fractional free volume in these solvents as a function of the composition. And we can make some comparisons and predictions to the gas selectivity. So we can look at the selectivity of CO2 versus methane. And we can look at that selectivity as a function of this fractional free volume. And we can map out this performance very, very well within this family of solvents. And so that's one piece of information. So we can make the strong connection between the pore structure and the solvation properties. But then also what we're able to do as well is look at the electrostatic potential within these systems. So if you're looking at separating different molecules, you can look at and think about it in terms of maybe a physical separation, in terms of this kind of pore size distribution, but then also we're interested in the differences in terms of the electrostatic interactions within these pore spaces. So even though the pore spaces might be the same, the interaction between a CO2 molecule that has a strong quadrupole moment versus a methane molecule can be very different. And so what we can do, very similar to the pore size distribution, is we can also calculate the electrostatic potential within these pore spaces. So this is just a snapshot of what this looks like. So we can map this out. And again, if you essentially drain the fluid from the system, you can look at these pores that are left in the system. And these pores are, again, where the gas molecules would absorb. And if you look at this, you get a fairly different picture of what these pores look like, from the bright red to the bright blue, depending on the local configuration and these electrostatic interactions in the system. So again, just like in our previous system where we're looking at the fractional free volume, we can also map out this electrostatic potential and use this to predict selectivity in the system as well. So this really gives us two different pieces of information. So number one, the pore size distribution or the pore structure, but then number two, this electrostatic information as well. And so we're now using this to look at membranes that are much more difficult to deal with than some of these liquid solvents. And so this is really what I want to focus on in terms of the kinetic Monte Carlo simulations that we're doing. And again, this is a multi-step process, but I really want to just kind of fast forward to the end here, where we're integrating some of the MD information with these kinetic Monte Carlo models. So I'll skip through this slide just for brevity, but this is really what we're focusing on here. So if we're looking at a membrane, there's several different things that happen, right? So you have gas adsorption on one end of that membrane, but then you have diffusion that happens through the membrane, and then those gas molecules will desorb on the other side of the membrane. And so you have differences in absorption properties, but then you also have differences in diffusion properties. And all of this is correlated. And so even though you might have a better absorbent for gas molecule A versus gas molecule B, that membrane or that polymer may not actually perform better because there may be some other limitations to the system. So we're trying to wrap all of this together within a kinetic Monte Carlo model to try to capture all of these steps. So this is the way that we do it. We take a molecular simulation, atomistic molecular simulation, and from that we map out the pore structure. And each one of those pores, we can evaluate the pore size and the connection from one pore to another pore. And depending on the pore structure, we can predict the relative rates of hopping. So the diffusion through these polymers or membranes are really best thought of as a hopping process. And so you can think of that as an activated process, which again blends very well with kinetic Monte Carlo. So we can put together this pore size map and this pore structure, and we can use this to describe the diffusion of different gas molecules through the system. So again, that's one piece of information. The other piece of information that we can take is we can also take that electrostatic information as well. So we can take information about the electrostatic potential in our system. And again, we can, with the exact same model, we can map that as well to our kinetic Monte Carlo simulation. So what we can do is we can blend those two pieces of information together. So we've got our pore size distribution. We also have our electrostatic potential information. And now we can perform these simulations very similar to what you would do in an experiment. So we can run these simulations as a function of temperature. We can change the partial pressure in the gas phase, and that's going to affect the adsorption on one end of the membrane. We can also change the polymer or the structure of the polymer. And the results from these simulations, we can get permeability of different ionic species or different individual gas molecules through the system. And we can get a lot of performance information on experimental timescales that we can compare directly to the experiments. So this is a very simple example of this. So this is kind of a test case that we can perform. And let me switch over to my laser pointer. So here we have the selectivity, and again, this is just kind of a toy example here. We have the selectivity of carbon dioxide versus methane. Okay, so this would be the adsorption selectivity to this membrane. So in one case, we set it as 1-to-1, so adsorption is the same. And then in the other case, we say that CO2 is going to be 40 times higher. And then what we do is we can run these simulations and we can look at the flux or permeability coming through this membrane. And when we do this, here, you can look at the relative flux. And if you look at the relative flux here in this column, even though we increase the adsorption selectivity of CO2 by a factor of 40, the flux only increased by a factor of 10. And if you look at kind of normal engineering design equations, that's very different than what you would get from normal engineering design equations, where it's usually just a factor of a product of looking at the adsorption selectivity versus the diffusion selectivity, and that will give you the permeability selectivity through the system. But in these systems, what happens is there's competition in the diffusion. There could be pore blocking in this diffusion. So there's a lot of atomistic and molecular level of events that you really can't capture in other ways. And so this kinetic Monte Carlo tends to be a very good bridge for making some direct comparisons to what's happening in experiment. So I've only got a few minutes left, but I want to briefly go through this very last project. So in this last project, I'll just give you a very brief background. We're looking at the formation of different tribological films on metal surfaces. So we're looking at just basically film growth on metal surfaces. And this is very important in engine applications in terms of trying to protect metal surfaces. And so there's a long history of looking at different molecules that will form these surfaces in different engine formulations. And so we're very interested in, how do you design these different engine formulations to grow different films on these metal surfaces? And so we have a lot of experimental data to compare with in terms of the film thicknesses, different additives that will affect the film thickness, and so on. And so our challenge really is to try to predict how this is happening at a molecular level, right? And so this is not trivial because we're really looking at kinetics that are happening on experimental timescales that are very difficult to capture on DFT or molecular dynamics timescales. We do have some DFT level information in terms of the events that are happening. So this is what we can use to populate our kinetic Monte Carlo model. So we can take some of these events and rate constants and activation barriers and use those to populate some of these larger scale simulations. And so this is really the heart of our method, is we're performing a hybrid kinetic Monte Carlo and molecular dynamic simulation. And this is really what it looks like if you look at the workflow on this right-hand side. So what we do is we have different events that will happen in kinetic Monte Carlo. So these are reaction events where these precursor molecules will come down to the surface, they'll decompose, they'll form bonds with their neighbors, and this film will grow. In the desorption, the side products will desorb from the surface. But when we do this in kinetic Monte Carlo, these systems or these films are stiff. So what we do is we cycle and take those configurations and cycle those back and forth into molecular dynamics. So when we take that configuration and we put it in molecular dynamics, we'll go through a short, maybe 1 nanosecond molecular dynamic simulation, which will relax those films. So if there are any local strains in the film, that short MD simulation will very quickly relax any of those strains. And then we put that back into kinetic Monte Carlo and we cycle through these loops of relaxation, reaction, relaxation, or reaction. We go back and forth, and this is all automated. And when we do this, we can make again atomistic level predictions about the growth in these systems at experimental timescales. This is a little bit about what this might look like. So we start off in these simulations with just a clean iron 110 surface. The first step is we'll just look for different adsorption sites on the surface. If you have a clean surface, there are a lot of adsorption sites available. So we pick one. One of our adsorbate molecules will adsorb onto the surface. The next thing we'll do is we'll just go back to our database and ask ourselves what can happen next. So next, that molecule can desorb from the surface, or maybe it can react with the surface, or maybe an additional molecule can adsorb on the surface. So again, we just cycle through this loop. And again, we go through this over and over again as this film grows. This is a little bit of information about the DFT, or I'm sorry, the MD simulations that are being performed simultaneously. So again, it bounces back and forth between KMC and MD. So in the MD stage, we use a force field. We have an empirical force field. We have partial charges that are updated with the QEQ method. You typically need a small time step for this because these systems can be unstable and they can blow up, so you have to be a little bit careful. Also, because you're adding molecules to the system, you have to recenter the linear and angular momentum in the MD systems, because you will get very, very slight changes in your system when you add or take off different products from the surface. And then this is a visualization of what this looks like. So let me change my pointer and play this. So when you run these simulations, what you'll see, and it's hard to see everything that's happening, but more and more molecules will absorb on the system, on the surface, and you'll also see changes in those molecules. So you'll see bonds being created. You'll see the side products, that crescent ring will pop off of the surface. And the simulation, again, will just bounce back and forth between MD and KMC. And this film will just gradually grow over time. And so you can get up to nanometer scale film thicknesses. And the nice part is, again, this is an example of the type of information that we can get. So this is an animated view of the composition of these films. So the very bottom in this graph is really just that, the bottom iron surface. And as you go up, that's the film as it's growing. And what you can do is you can monitor the composition of that film, elemental composition. So carbon, oxygen, phosphorus, hydrogen, you can get a lot of atomistic information about that system. We can compare experimental growth rates. So we take our KMC, we get very similar growth rates to the experiments. And then we can also perform some, here in this case, we can generate a simulated AFM image of our films as they're growing and compare that to experiments, and we get some very similar features. We're still about an order of magnitude off in size. We're not quite able to get as large as the experiments, but again, we're able to get pretty close and capture a lot of similar features in the experiments. So I'll conclude here. I know I've gone very quickly through several different applications, but what I really wanted to do is really just emphasize the timescales that can be extended in some of these types of systems. You know, not just the traditional catalytic systems that people have looked at in the past, but you can apply this to some of these soft amorphous films and get a lot of information. And really the driver behind all of this is so many of these systems that you encounter are driven by kinetics. And so many of the questions that you get asked by an experimentalist involve kinetics. And so this is a really good bridge and a really good way of taking a step forward in terms of taking some of those atomistic molecular level features and preserving those features, but still achieving some of these extended timescales. And so last of all, I'll just end with some acknowledgements from funding sources, NSF, DOE, Acton Chemical, Supercomputing Time. I've got a snapshot here of my research group, and then a lot of the experimental benchmarks that we've used over the last several years have come from Jason Barra here at UA. He's performed a tremendous amount of synthetic chemistry to make these polymer solvents and ionic liquids. So he's been a tremendous resource for me over the last several years. So with that, I'll thank you for your attention, and I'd be glad to answer any questions about my work.
Thank you so much, Professor Turner. We are now open for questions. If you want to ask one, please enable your microphone, or you can write questions on the chat. And our YouTube viewers can also ask questions on the chat. Professor Jin wants to be the first. You can go ahead.
Yeah, thank you, Professor Turner. It's a very interesting talk. I really enjoyed it. And I have one quick question about the CO2 capture using the ionic liquids. In that model, it seems like you consider the ionic liquids a rigid model. So my question is whether we need to consider the flexibility of the ionic liquids through this CO2 absorption or the desorption or absorption process. If this flexibility is important, is it possible that your kinetic Monte Carlo simulation can consider this effect?
Yeah, it's a really good question. That's something we've, I guess, kind of grappled with as we've been developing our models. So if you're looking at some of these kinetic Monte Carlo models, a lot of them adopt a kind of a rigid configuration. Either you're connected to a lattice and restricted to that lattice, or even in our off lattice configurations, we're still dealing with a rigid model. So that flexibility can be very important. And people have actually shown that with some of these membrane applications, that some of that, some of those diffusion events will correspond to some windows opening and closing within some of those membranes. And so we've talked about and thought about different ways of incorporating that. And so kind of my thoughts are that there are different ways that you can actually, take several different kind of kinetic Monte Carlo models, develop those kinetic Monte Carlo models based on, maybe a dozen different snapshots, maybe 100 different snapshots from the MD simulations, and use those as different configurations in the kinetic Monte Carlo model. So not necessarily relaxing the entire model, but at least providing some degrees of freedom in terms of maybe cycling or in terms of incorporating, different connectivity between, the different spaces, or changing on the fly some of that pore structure in the model.
Okay, thank you so much.
Yep.
Who wants to ask a question? Okay, go ahead. Go.
Thank you very much for your talk, Professor Turner.
Thank you.
Very challenging, your approach. I am a membrane experimentalist, and I was really, you strike a chord when your approach was trying to model structure with forces. I have two short questions. The first one, are you able to take in account the effect of concentration, or all your simulation are based on pure data on the pure gases, CO2, for example, and methane? And the other question has to do with the stability of ionic liquids in polymer membrane. Are we able also to predict what will happen with interaction of ionic liquids and the polymer molecules with time?
Yep.
I mean, it's time stability, which both problems are very actual and limiting problem in the application of membrane technology to CO2 separation, specifically at maybe some higher pressures.
Yeah, those are both great questions. So in terms of our membrane models and our kinetic Monte Carlo models, your first question was about the gas phase. So we have a lot of control over the gas phase composition, or that gas phase partial pressure. So in our model, the way we handle that is, and this is typically what people do with the surface science types of models where they're looking at catalysis, is we'll have different rates of collision with that surface, depending on again, the partial pressure, the relative concentration of different gas species in the system. So we can look at very high concentrations, very low concentrations, and we can look at mixtures. And what that will dictate is that will dictate the relative rate that that molecule will be hitting that membrane surface. Along with that, there's going to be a sticking probability. So just because it hits the surface doesn't mean it's necessarily going to stick to that surface. And so we can also put in information about the sticking probability. And again, this is the approach that most people take when they're looking at heterogeneous catalysis, looking at gases on solid surfaces. Okay. Your second question was about the ionic liquids with the polymers and about stability and maybe the interaction between these systems, which is also a really good question. In my opinion, computationally, we're not very well equipped to answer that question. So, in our models, we can put the ionic liquids, in those membranes, and they actually interact very favorably. That's one of the reasons that we're looking at these ionic polyimides, is because these ionic polyimides have this charge group along the backbone. And because these ionic polyimides are naturally charged, they tend to interact very well with these ionic liquid molecules that will add to the system. If you have other types of membranes, you might get some blowout. And I'm speaking, I'm just regurgitating some information that I get from some of my experimental colleagues, mainly Dr. Barry here, is with some of the other applications where they've tried to incorporate some ionic liquids and other membrane platforms. If you go up to high partial pressures, those ionic liquids might over time end up blowing out or leaving, but in these ionic polyimides, they're very stable. But in our simulation models, we really don't look at those types of performance issues. We're really not able to look at any type of like chemical degradation, at least not now. We're not incorporating that into our system. So, some of these ionic liquids, they can degrade as a function of time, but we're not capturing that in our model at this point. We really rely on our experimental colleagues to measure that for us. We feel like they can do that well, and really don't need our help necessarily in that regard.
Thank you for clarifying the question.
Professor Haja wants to ask a question. You can go ahead.
Thank you, Professor. Can you hear me?
Yes, I can hear you well.
Thank you for very interesting lecture. Again, my doubts are on your comments on membrane. First of all, we think of common membranes like polyethylene or polyimide. The glass temperature is somewhat important. And you use adsorption and solubility interchangeably. How important is the solubility? The way we understand is, at least I understand, is diffusivity increases with temperature, but solubility can decrease very much. Okay, so it depends on the glass temperature of the polymer or the membrane. What are your comments on it? Is it really true, or especially at high pressures, can it revert?
Yeah, so I don't know if I've got anything profound to say in that regard. I would say that I would agree with you in terms of some of your comments. So when we're looking at the kind of general performance of these membranes, what we'll do in simulations is we'll look at different characteristics of some of the monomers, and we'll even look at some of the short chain polymers as well in simulation. So we'll look at, we'll predict things like glass transition temperature or radius of gyration, and we've made some comparisons and compared that to performance. I think there are very strong correlations between the glass transition temperature and some of the diffusion behavior. I think that tells you a lot about the kind of relative flexibility of the polymer, especially down at kind of the molecular scale, because in my opinion, when you're looking at the diffusion of gases in these systems, it's really, I really see it as a hopping. So you're really looking for that window to open to get from one point to another point in that polymer or in that membrane. And to me, that has a lot to do with that glass transition temperature, or how close you are to the glass transition temperature relative to that polymer. So I'm not sure if I really answered your questions. I probably have more questions than you do at this point about some of these interactions and behavior of these systems. But to me, one of the most important part about our investigation is just keeping a very open communication channel with our experimentalists to learn what they're learning about the performance of materials.
Professor Richard wrote a few questions on the chat. Would you like to ask?
Sure. So I guess, are we getting background noise or something? Can you hear me?
Hey.
Hi, how's it going, Heath? Long time no see. Very good. How are you?
Good.
Yeah, so I posted those in the chat, but I guess you might need to close your share in order to see the chat.
Yeah. Let me see. Okay.
some of them reflect my naivete. And so I was expecting to see some kind of response surface or free energy landscape, and there would be some smoothing of those high frequency events. I was wondering, do you use Kalman filtering to smooth that out, or just kind of eyeball it? And well, what do your free energy landscapes look like? Do you not show them because they're too multi-dimensional? You just can't visualize them? Why didn't I see any free energy landscapes?
So that's a good question. I don't know that I necessarily have a good answer for that one either. So I would say it's very system dependent. So, we've, in the projects I went through, we've looked at, several different material platforms, and each one's going to have really the question that we ask ourselves, and this is really kind of cast within in the kinetic Monte Carlo framework, is to really kind of ask yourself, what are the most important events that are happening in the system? So there are going to be these kind of high frequency, vibration modes or parts of this potential energy surface that you're just not going to see. You're just not going to capture. And so with us, and that's part of the empiricism of the kind of kinetic Monte Carlo approach, is that, you might put together a model like this. You might run it, and it might work well, or it might not. And if it doesn't, that's really what kind of prompts you to ask yourself, okay, we kind of put together this database. We have, maybe a dozen different events that are happening in the system. Maybe some of these minor events that we think of being minor events really aren't minor. Those events might be the ones that are really propagating the system in time, even though they might be those events that, again, initially you might have thought of as being trivial. Those might be critical to the overall potential energy surface. So again, that's kind of the mindset or perspective that we take. So we really don't map out like a full kind of potential energy surface for these processes. If we had a simpler system, and if you look at some of like the heterogeneous catalysis systems, where they might look at just NO decomposition on a 1-1-1 surface, they can run some very precise DFT calculations, and they can map out that free energy surface pretty well, and then just plug that right into a kinetic Monte Carlo model. We have too much. Our systems are just too messy to deal with that. But kind of our logic is that if we're able to capture those quintessential events, that we are going to be able to capture those physics that are most important to making real predictions on real experimental timescales.
Well, okay, so I guess what you're saying is there's just way too many factors to map that out.
Yeah.
But what are the factors then? So I guess you're saying that if it was just a catalytic analysis of a surface, you could just map X and Y, and then you'd get all the positions of all the atoms, and that would be all you need. But is that for your system is not? Well, I guess there is a surface, but it's not. The surface is not what's dictating the kinetics that you're searching for. So plotting X and Y would not be relevant for you. So what are because those are going to be relatively smooth, I think, relative to your events. So what are the factors that are? Do you know what I mean by when I say factors?
To an extent. Again, I think it is going to be very maybe system dependent. If we're looking, so if we're looking at that kind of membrane polymer system, that kind of, I guess, second project, if we're just looking at like the gas adsorption on the surface, for instance, what we would do in that case, and what we have done, is we can perform some molecular dynamic simulations. And what we can look at is we can look at, what is the, relative, solvation or adsorption of, CO2 versus methane in that, on that polymer surface. And so from that, that will give us, we can potentially get an adsorption rate or get that, sticking probability from that, and, simultaneously get a desorption rate, depending on how strongly it binds, to the surface. So essentially what we're kind of taking this extremely complex free energy landscape and just narrowing down, basically taking many dimensions out of this free energy landscape and looking at just a few of those dimensions, if that's maybe a better way of thinking about it.
So adsorption rate and desorption rate are the two key energies that appear in your kinetic model.
Right.
And so if you just get those two things, that's all you need. And
to an extent, that's not all. I mean, that's part of it, right? So that basically would tell you, what's happening at that surface or at that one face, right? So other events that are happening is those gas molecules are going to be diffusing from one site to another site to another site, all the way through that polymer. And so there needs to be information about, what is that, in our perspective, what does that pore network look like energetically? So again, we don't have, or we're not using, it's basically if you want to think about it as kind of like a coarse-grained pore network, right? So when we're taking our molecular dynamic simulations of this polymer system, and when we're developing this pore network, we're really coarse graining it. So we really have these pore spaces. And so we're really getting some information about, what does that kind of coarse grained site, look like in terms of a pocket in the system. And then again, at the other face, you'd have desorption. But then also, I mean, there's all the correlations that happen within the membrane itself in terms of the interaction between adsorbate molecules, again, like I said, pore blocking or other events that might happen.
I wonder if you couldn't pick out a few things, like you've characterized void sizes. So if you had some sort of void size factor, okay, and then the mirror image of that is, I think you could find, is the filled size, okay? So how big is that? And so if you were to map your energies as a function of those two things, okay, then in terms of the hopping, you would be able to map out versus those two dimensions, and then you could see things. And why I worry about that is, you're kind of prejudging and pre-assuming that there's going to be just these kinds of events.
Yep.
Whereas if you look at all the surface, you might see that there's some kind of event over here that you didn't, or the shape is more like a saddle or something like that you didn't fully appreciate.
Yeah, it's true. And again, that's kind of the crux of these simulations is that they're not predictive, right? So, but we do run, MD simulations where the kind of the idea is we're looking for, what is possible, right? So what are events that are likely to happen? What are the adsorption sites, right? And again, we're taking that, molecular dynamics three-dimensional structure to make these pores. These are not arbitrary pore structures that we've kind of knitted together, but these are based directly on MD simulations. So again, our thoughts are these pore structures and the electrostatic potentials that are mapped onto these pore structures. This is what the gas molecules are going to feel. So if they're in that pore, this is kind of like their little local pocket that they're seeing. And again, by doing this, that's really the only way that we're able to extend to these, large scales. If we start expanding those degrees of freedom, in other ways, then very quickly you go from minute time scales right back to nanoseconds.
Yeah, okay. All right, I think I got the idea there. Just a quick question. You were saying how so many of these ionic liquids are too expensive.
Yep.
But I heard about a long time ago, actually, these like amino acid based ionic liquids where something like threonine is really cheap because it's used in animal feed. And then you can make an ionic liquid out of that. But I think threonine was too viscous. But are there other thoughts along those lines of starting with cheap raw materials and making ionic liquids out of that?
Nope. That's my conclusion based on a lot of discussion with a lot of experimentalists. So it really comes down to, at this point, nobody has been able to get around the viscosity issue. And people have been working hard. This is not a new challenge. People have been working on this for many, many, many years. And I think it's just the nature of the compounds, the viscosities are high. And even if you're looking at raw materials, a lot of it ends up being to the multi-step synthesis that you need to get to these ionic liquids. And again, there are other challenges as well in terms of stability and corrosion, and a lot of them are hygroscopic and absorb water. So in terms of, to me, this kind of bulk, large scale industrial application, ionic liquids are one of the worst candidates you can come up with in terms of CO2 selectivity. If you start getting into more niche applications, I think that's where you've got lots of possibilities. If you're talking about separating proteins and separating other, pharmaceutical ingredients, then the sky's the limit in terms of cost. But in terms of large industrial applications, I think it's very difficult.
Well, and then why is viscosity such a problem if you're trying to make a membrane?
It's not, and so that's kind of that's why we're exploring some of these membrane systems. Is okay, can we capture some of this, selectivity that people have seen with these ionic liquids and these kind of similar ligands, and can we kind of build it into this membrane system where you don't have to worry about pumping anything, at least not the liquid. You might have to add a little pressure to get the air to flow, but you have shorter diffusion paths, and there's a lot of advantage. And these membranes can be much cheaper. The kind of the polymer structures can be fairly inexpensive. So,
does the diffusivity drop as the viscosity goes up?
It tends to. Yes. Okay. What experimentally, and we haven't done this computationally, but what they found is they can actually take some of these membranes, these ionic polyimides, add ionic liquids to them, and actually increase the diffusivity by an order of magnitude. So just some of the thoughts are, some of the ionic liquid addition might plasticize the polymer a little bit and increase that diffusivity. And that kind of went back to one of the questions that was asked earlier in terms of the TG. So there are some of these interactions that can help, even though it might be counterintuitive in certain cases. So.
And then my last question was, we looked at silicalite, which is a kind of an inert form of zeolite, a long time ago. And what we found for that membrane was there were significant entrance and exit effects. This might be another thing you kind of answered already, but you're treating the entrance effect as essentially a sticking coefficient or an adsorption coefficient. Okay, so if it sticks, it enters. Done.
Not necessarily. It can desorb. It goes both ways.
Oh, okay. Yeah. Okay. So, but in a zeolite pore, you have to find where the pore is. But in your surfaces, you don't have those kinds of well-defined pores. Is that?
No. They are well-defined. So even if you adsorb on the surface, you could kind of diffuse around on the surface. So in other words, you're not necessarily finding that manhole, right? You're not necessarily falling in until you find it and then pop out on the other side. And then once it pops out onto the other side, it can diffuse around on that surface as well until it gets enough energy, and pops off.
Okay. And you have a streaming velocity for this?
In terms of, so we have a pressure gradient in the system, which drives the diffusion or the flow through the system.
So what we found, and this is actually something Ed McKenna developed, was if you don't assign a streaming velocity, which is sort of that reflects the average flow of the molecules are going from one place and ending up in another.
Yep. Yep.
And if you don't do that in your reservoir of molecules, then you get a discontinuity in your fugacity when things leave the reservoir and go into the vapor space. And then that throws off some of the calculations. And so that was one thing that was important for us to correct for. Something to look for that is basically where we figured out or inferred this effect was plot 1 over your flux versus 1 over your membrane length. So you've got to vary your membrane length. Yep. And so what the non entrance effect is going to be linear as you make that thicker membrane thicker, right?
Yep.
And so what you'll see is that there's you have to make it a certain level of thickness before it actually becomes linear. Right. And that thing that's residual, that 1 over flux versus 1 over length, the intercept won't go to 0.
Right.
And so that deviation from 0 is your entrance effect.
Yep.
And have you made that plot then?
I haven't done it with this model. I've done it with some other systems in general, but I understand what you're saying. It's almost like the circuit model, right? Where you have a capacitor, resistor, and you can kind of go through a frequency analysis, frequency response analysis, and you can kind of identify different limiting factors of your circuit, if you want to think of it that way. So yeah, it's a good point.
Okay, thanks.
If we don't have any more questions, I think it's time to wrap it up.